In this part, we look at the actionable insights proposed. I thought this section of the paper is really insightful as the authors, after framing existing works in CoALA, spotted some gaps that are important and underexplored. They also discuss open questions which are good food for thought. I highly encourage the viewer to read the paper as they cover quite a lot in this section. As such, I'll only cover a few points which I thought were the most important. In the author's opinion, the most important suggestion is that agents should be structured and modular. Standardized terms allow for conceptual comparisons across works. For example, in the Markov decision process, we have the state, action, transition, and reward. Without this, it can be confusing to remember the specific term in each research paper when they all refer to the same thing. Standardized abstractions facilitate experimental work when using frameworks. For example, in the OpenAI gym, the environment class returns the observation, reward, done, and info when an action is stepped through. The authors think that it's timely and impactful to implement abstractions for language agents, for example, the memory, action, and agent classes. Lastly, common libraries can reduce technical debt by facilitating testing and component reuse. It can also standardize user experience instead of having the user interact with a mix of agents developed by individual teams. On a side note, if you're looking for examples of implementations, I'll be releasing elements of my attempts at cognitive architecture over time. The repo will be linked in the description below. The most direct actionable is designing agents with CoALA. One can look at the diagram and ask, which components need to be implemented and how should they be configured? So let's take the example of designing a personalized retail assistant. The first step is to determine memory modules. Our retail assistant needs to track the dialog state in the working memory. It needs to store the customer's purchase and interaction history in the episodic memory, items for sale in the semantic memory, and the ability to query data stores in the procedural memory. Then, we need to define the action space. Recall that in CoALA, actions can refer to learning, retrieval, and reasoning. Our retail assistant needs to be able to retrieve from all three memories, but only write to episodic memory to store new interactions. It shouldn't be able to alter its own skills or the items for sale. The last step is to define the decision procedure. So our retail assistant, upon receiving instructions from a user, retrieves the user interactions from episodic memory for a prior over their intent. It also retrieves the list of items for sale and reasons if any of these items will meet the user's requirements. It then replies to the user and at the end of the interaction, learns from the interaction history to be more personalized to the user in the future. On a side note, I think this diagram has two additional uses. The first is, if you already have an agent which does not have all the components here, ask if would adding any of these elements make your agent better. The second is, if you have a task for an agent, are there any elements here which the state of the art is still lacking so that you can focus on improving that element? The next actionable insight is to think about how LLMs can perform structured reasoning beyond prompting. One must remember that language models by default are trained for language tasks. It is geared towards fluency and not necessarily reasoning. However, a lot of interest in LLMs was spurred from its apparent reasoning abilities, and researchers have been attempting to find techniques that improve such capabilities. Such reasoning use cases can inform model training. For example, are there ways to train or fine-tune LLMs towards these reasoning modes, such as chain of thought? This point is quite prescient as after the publication of the paper, OpenAI's O1 has renewed interest in this area. While they did not reveal the full technique, I quote from their online post, "Learning to reason with LLMs," where this image is from, that their O1 model is trained on reinforcement learning that teaches the model how to think productively using its chain of thought. And as you can see on the left image, this new training mode scales with time. This seems to be based off an earlier paper, Let's Verify Step by Step, which trains a process-supervised reward model to predict the correctness of intermediate reasoning steps rather than just the final result, which is important for tasks that require multiple steps of reasoning. As LLMs reason and produce new knowledge, the authors ask, how can agents effectively use this produced knowledge on top of existing human knowledge, enabling efficient lifelong learning? They gave an example of a coding agent which starts off with knowledge from textbooks and manuals, and as it solves problems, stores the experience in its episodic memory, and after it reflects over its successes and failures, stores the new lessons in its semantic memory, and it also stores useful methods like quicksort and other algorithms in its procedural memory. In fact, some of the authors on the CoALA paper were also co-authors on this paper, Can Language Models Solve Olympiad Programming?, where to facilitate this coding agent idea, they released a benchmark based on the USA Computing Olympiad, provided textbook data, and tested out some techniques such as the one in the image here. To reiterate from previous sections, the authors encourage us to think about how agents can learn beyond in-context learning or fine-tuning. First, how can the procedural memory, which holds the skills to do things like learning, retrieval, and reasoning, be modified over time? The authors suggest that agents can learn better retrieval to make better use of experience. When an agent learns a new piece of knowledge, it could reason about when the knowledge will be useful, so that it can be appended as metadata to facilitate future retrieval. Next, are there new forms of learning or unlearning, the pruning of knowledge? Can we use smaller models for reasoning subtasks? Now that there are multiple forms of learning, each for its respective type of memory, what are some new interactions that could result from this? The next major theme is decision-making beyond action generation. For example, in decision-making, can we combine language-based reasoning and code-based planning? Because existing works mostly reason and plan in language or translate from language to world models and then plan and reason from there. Could future agents write and execute simulation code to evaluate plans? Again, this point is quite prescient as in 2024, there are some papers that suggest that LLM's planning ability is mostly from memorized details and classical planners should be used when possible. The next part on thinking about decision procedures is meta-reasoning to improve efficiency, which really reminds me of this XKCD comic over here. How do we balance the cost of additional LLM calls versus the improvement of the plan? Current methods usually use a predefined budget. For example, in tree search-based methods, the depth is predefined. On the other hand, humans adaptively allocate computation. The effort in thinking about 1 + 1 is different from the effort in solving a partial differential equation. Once we manage to find a meta-reasoning algorithm to balance the cost, how can we modify the decision procedure accordingly? Actually, I think the same principle applies to the amount of compute in reasoning and the retention of memory chunks.